You're about to hear a lot of headlines about a doomsday fish that washed ashore in Denmark. You're about to hear a lot of speculation about a small earthquake that registered nearly 60 miles down off the coast of Italy. And almost every single one of those stories will miss the actual point. Because hiding under the Mediterranean, between Italy, Sicily and the Aeolian Islands, sits a mountain. Taller than peaks in the Alps, active, capable of sending a tsunami into the Aeolians in roughly 10 minutes, and Calabria and Sicily in 20, without a single felt tremor to warn anyone. Its name is Marsili. Most people have never heard of it. Stay with me. By the end of this video, you will understand exactly why that is a problem. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you are watching from. Let's get into it. Part 1. The data drop. There is a number sitting in a seismic database right now that almost no one is talking about. A magnitude 2.7 earthquake, roughly 96 kilometers down, logged in a stretch of water between mainland Italy, Sicily, and the Aeolian Islands. On paper, it is nothing. It is the kind of tremor that doesn't crack a coffee cup, doesn't wake a sleeping dog, doesn't even register as a flicker on the surface of the sea above it. It is, by every conventional measure, statistically boring. And yet, if you understand exactly where that quake happened, and exactly how deep it went, and exactly what is sitting almost directly above it, the boredom evaporates, because that little tremor lit up a zone that most people, including most Italians, have no idea exists. A zone where the largest active volcano in Europe is hiding under 3,000 meters of water. A volcano taller than a mountain in the Alps. A volcano with a summit sitting only about 500 meters below the sea surface. A volcano that, according to peer-reviewed modelling, could deliver a tsunami to the Aeolian Islands in roughly 10 minutes, and to the coasts of Calabria and Sicily in roughly 20, without a single felt earthquake to warn anyone first. Welcome back to Project Nightwatch. I want you to hold on to that contradiction for a moment. Too small to feel, too deep for typical volcanic plumbing, and yet positioned with surgical precision inside one of the most geologically loaded regions on the European continent, the Tyrrhenian Sea. A body of water most people picture as a postcard. Turquoise coves, white-painted villages, lemon trees leaning over balconies. What they don't picture is the engine running beneath all of it. A subduction zone, a back arc basin, a chain of volcanic vents, and a hidden giant called Marsili. And then, almost as if the universe had a flair for dramatic timing, another piece of news started circulating online. A so-called doomsday fish, an oarfish, had just washed ashore in Denmark. Not long before, another one had appeared in Ireland. Long, ribbon-shaped, silver, alien-looking creatures from the deep ocean. The kind of fish that fishermen used to whisper about. The kind of fish that, in old Japanese folklore, was said to surface only when the seafloor itself was about to convulse. The kind of fish that, in 2026, becomes a viral video within hours. So you have, in the same news cycle, a tiny earthquake under a hidden volcano and an omen species washing up on European beaches. And the internet, being the internet, immediately did what it always does. It welded those two things together. It wrote the headline before the science could even open its laptop. Here is the question I want you to sit with. Are these two events actually connected? Or are we doing what humans have done since we first started staring at the sky? Pattern matching, story building, taking unrelated dots and drawing a line between them because the line feels meaningful? Because here is the catch. The Italian National Institute of Geophysics and Volcanology, the agency responsible for monitoring this exact stretch of seafloor, has not issued any alert. There is no escalation, no flag, no anomaly bulletin. By their reading, this earthquake is routine. The system is doing what subduction systems do. The fish are doing what fish sometimes do. Move along, nothing to see here. And yet, something about this moment is gnawing at people. There is an instinctive, almost ancient unease when small signals start clustering. Science says coincidence. Intuition says context. And the truth, as it often is in this channel, sits in the uncomfortable space between those two readings. Because here is the part that almost everyone reporting on this story is missing. The real risk under Marsili was never going to announce itself with a magnitude 2.7 tremor. It was never going to be telegraphed by a fish on a Danish beach. The real risk doesn't need a precursor. It doesn't need a warning sign. And that, more than any earthquake or any omen species, is exactly what makes it dangerous. So which is it? Are we misreading coincidence, or are we overlooking something far more important sitting underneath all of it? Part 2. The depth problem. Let's talk about that 96 kilometers, because that number is doing more work than people realise. To most viewers, an earthquake is something that happens in the crust, a few kilometres down, maybe 10, maybe 20 in some big events. Plates grind, faults slip, the surface shakes, buildings sway, and the whole event lives in your immediate neighbourhood. That is the mental model nearly everybody walks around with. A quake at 96 kilometres down is something else entirely. That is not crustal shaking. That is well below the Earth's outer skin. That is down inside a slab of oceanic lithosphere that is currently sliding into the mantle. We have a name for earthquakes like that. We call them intra-slab events, meaning the rupture is happening inside the descending plate itself, not at the boundary where two plates meet, and not in the brittle surface layer where most everyday seismicity lives. To understand why an intra-slab quake under Marsili matters, you have to picture what's actually happening beneath the Tyrrhenian Sea. Off the coast of southern Italy, a piece of seafloor called the Ionian Plate is being shoved downward beneath Calabria. It is descending at an angle, slipping into the hot interior of the planet at speeds that, geologically speaking, are aggressive. As it goes down, it carries with it water. Water trapped in minerals, water bound up in sediments, water that has been a passenger on this slab for millions of years. And as that slab descends and the temperature climbs, that water gets cooked out. It is squeezed out of the rock under enormous pressure. This is called slab dehydration, and it is one of the most consequential processes on the planet that almost nobody outside of geophysics talks about. Because when that water escapes upward into the overlying mantle wedge, it lowers the melting point of the rock above it. It triggers melt. It creates magma. And that magma is what feeds the volcanoes you've actually heard of in this region. Mount Etna, the largest active volcano on continental Europe. Stromboli, that little spitting island off the Aeolian coast that has been erupting more or less continuously for thousands of years. So that small earthquake at 96 kilometers down is not just a stress release. It is happening inside the very system that manufactures Italy's volcanoes, which is why, even though the magnitude is tiny, the location and the depth combine to make scientists pay attention in a way that the surface noise of social media never will. Now, here is where I have to be brutally honest with you, because that is the deal we have on this channel. The truth is, we don't know if this specific quake means anything for Marsili in the short term. Could be entirely routine slab stress, the kind of crack and pop that happens deep in subduction zones every single day around the world. Could also be a tiny piece of a much longer process that, over centuries or millennia, helps load the magma plumbing system feeding the volcanoes above. Both interpretations are scientifically valid. Neither one says the eruption is tomorrow. And here is the other thing you need to understand. Deep earthquakes don't really produce the kind of surface warning signals that people hope for. They don't shake your house, they don't break dishes, they don't trigger early warning sirens. They are a whisper from the lower lithosphere, and you only hear them if you've got the right instruments pointed in the right direction. Whatever influence they have on overlying volcanic systems is slow, indirect, and very hard to isolate from the background hum of the Earth, which raises an unsettling thought. If this quake is too deep to matter quickly, and too small to matter loudly, then what exactly is the thing we should be watching? Because the central question of this entire investigation is starting to take shape. The earthquake under Marsili is not the threat. The earthquake is the thing that pulled our attention toward the actual threat. And the actual threat, well, that doesn't need any earthquake at all. So if it isn't the quake, what is it? Part 3. The Etna Echo. While that deep tremor was logging itself into the database under Marsili, something else was happening a little further south. Another small earthquake, this one west of Mount Etna, at a depth of roughly 33 kilometers, shallower than the Marsili event but still well below the level of typical crustal shakes. Two small signals, two different parts of the Calabrian arc system, basically simultaneous in geological terms. Now, Etna is a beast you've probably heard of. It is one of the most studied volcanoes on the planet, partly because it sits right next to a major city, Catania, and partly because it almost never shuts up. Its plumbing is famously complex. It has multiple feeding systems, lateral chambers, gas-rich magmas, and a temperament that has produced everything from gentle lava fountains to violently explosive paroxysms, and underneath all of that, it is hooked into the same subduction engine that makes Marsili what it is. So when an earthquake pops at 33 kilometers depth on Etna's flank, you've got at least 3 plausible interpretations sitting on the table. Interpretation 1, it is just normal tectonic stress release, a piece of crust adjusting to the constant grinding of the plates. Interpretation 2, it is a deeper expression of slab-related deformation, related to the same Ionian plate processes we just talked about. Interpretation 3, it is magmatic fluid movement, a sign that something is shifting in the system that feeds Etna's vents. In scientific terms, all 3 are live possibilities, and pulling them apart requires careful analysis. Etna has a long history of subtle precursors before larger events. Small swarms, gas changes, ground deformation that you wouldn't notice unless you were measuring with millimetre precision. None of which, I want to be very clear, is currently flashing red. Etna's monitors are not screaming. Catania is not on alert. The volcano is doing what volcanoes like Etna do, which is constantly murmuring under its breath. What is interesting is the clustering. You have a deep event under Marsili. You have a moderately deep event under Etna. They happen in the same window, and if you zoom out far enough on the map, you start to see that they are sitting in the same regional stress field, both connected to the same descending slab. That doesn't prove anything causal. Earthquakes cluster all the time, sometimes by random chance, sometimes because of genuine stress redistribution between linked systems. But this is exactly where I want to bring you back to the spine of this story, because if you look at Etna activity in isolation, you can write a perfectly reasonable explainer about it that has nothing to do with Marsili. You can talk about lava and tourists and the romance of volcano watching, and in doing that you do exactly what most coverage of this region does. You miss the fact that Etna is a flashing neon sign and Marsili is a hidden one. Etna gets the cameras. Marsili sits in the dark 3,000 meters under the water, doing whatever it is doing without anyone watching. So Etna's little echo here isn't important because Etna is about to erupt. It is important because it is one more small signal in the same regional system, one more reason to take a hard look at the part of that system that we cannot see, the part with its summit 1,600 feet under the sea. And that is where this story keeps quietly pointing. What other small, almost invisible signals have been showing up around the same time? Part 4, the Oarfish trigger. Here is where the story leaves the seismograph and goes for a swim, because in the same window of time as these tremors, photographs started circulating of an oarfish washed up in Denmark. And then people remembered the one in Ireland not long before that. Long, silver, ribbon-shaped, with a red crest and an eye like a small moon. Even if you've never seen one before, when you do, your brain immediately knows you're looking at something that does not belong on a beach. In Japanese folklore, the oarfish has a name that translates roughly to messenger from the sea god's palace. The legend goes that when these creatures appear on the surface, the seafloor is about to move. The story is centuries old. It survives in part because every now and then, an oarfish would beach itself shortly before a major earthquake, and humans, being meaning makers, locked that pattern into cultural memory. When 2 of them show up on European coasts at the same time, as a deep tremor under Europe's largest hidden volcano, you can see why the internet went into pattern-matching overdrive. The headline practically writes itself. Doomsday fish predicts disaster. Marsili awakens. The omen the scientists ignored, and it spreads at the speed of a swipe. Here is the strongest version of the argument, and I want to give it a fair shake before I take it apart. Oarfish live in the mesopelagic zone, the twilight depths of the open ocean, hundreds to 1,000 meters down. They are not built for the surface. They are not strong swimmers. Their bodies are fragile, so whatever brings them up has to be unusual. Proponents of the prediction theory argue that something disturbs them down there, some pressure shift, some acoustic event, some change in chemistry, and that whatever causes their stranding might also be a precursor to seismic activity. It is a tidy story. It is also, when you actually go look at the data, not really supported. There is a study by Grant and colleagues published in 2019 that looked at exactly this question, comparing oarfish appearances against earthquake records over many decades. They found no statistically meaningful correlation. Strandings happen for plenty of reasons that have nothing to do with the seafloor twitching. Illness, disorientation from currents, storms, post-mortem drift. A fish that died at depth 3 weeks ago and finally washed in. The list is long, and most of it is mundane. So why does the Oarfish narrative still feel powerful even after the data says coincidence? Because of something cognitive scientists call availability bias. When an Oarfish shows up before an earthquake, we remember it forever. When 10,000 Oarfish show up and nothing happens, we don't even hear about it. The hits get amplified, the misses get forgotten, and over time the brain assembles a pattern that doesn't actually exist in the numbers. And then there are the viral electric field claims. The idea that Oarfish can detect tiny electrical shifts in the water caused by stressed rock deep below, and that this is how they sense an oncoming quake. It is a beautiful theory. It is also, at present, completely unsupported by direct measurements. We don't have data showing the relevant electric fields exist at the relevant amplitudes at the relevant times. We have a story that sounds scientific dressed up to look like one. Now, here is the part where I bring you back to why any of this matters for tonight's investigation. The Oarfish narrative is doing something specific to your attention. It is pulling your eyes upward, to the surface, to omens you can photograph, to stories you can share. And while it does that, the actual hazard under the Tyrrhenian Sea, a sleeping giant called Marsili, sits exactly where it has always sat, 3,000 meters under the water, completely unseen, completely unphotographable, completely uninterested in our folklore. The fish are not the warning, the fish are the distraction. So if the fish are not the story, what is? Part 5. The real hook. Let's pivot, hard. Forget the fish. Forget the magnitude 2.7 for a moment. Forget the Etna echo. I want to introduce you properly to the actual subject of this video, because it has a name, and almost no one watching this knows it. It is called the Marsili Seamount. Marsili, remember that name. It is the largest active volcano in Europe. Bigger than Etna, bigger than Vesuvius, bigger than anything most people will ever picture when they think of European volcanoes, and it is hidden. Not metaphorically hidden, literally hidden. Its summit is roughly 500 meters below the surface of the sea. About 1,600 feet of water sit between its crater and the sun. Stop for a second and let that sink in. Imagine a mountain, not a hill, not a bump on the seafloor, but a full-scale volcanic edifice, taller than peaks in the Alps, sitting in the middle of the Tyrrhenian Sea between the boot of Italy, Sicily and the Aeolian island chain. You could fly over it on a beach holiday and never know it was there. You could swim over it on a yacht and never feel a temperature change. The water just stretches on, blue and untroubled, completely opaque to everything happening beneath. This invisibility is not a quirky travel fact. This invisibility is a hazard category in itself, because you cannot do visual monitoring of a volcano you can't see. You can't fly drones over its crater. You can't watch its plume. You can't measure its glow at night. Everything we know about Marsili, we know second-hand, through ship-based surveys, through occasional submersible visits, through magnetic measurements, through a handful of seafloor instruments that have to be deployed and recovered with significant effort and expense. And here is the thing I want every viewer to understand, because it is the entire reason I'm making this video. The most dangerous thing about Marsili is not necessarily an eruption. The most dangerous thing about Marsili is what scientists call a flank collapse. A piece of the volcano's side breaking off and sliding down into the surrounding basin. And when that happens, if that happens, the consequences are not measured in lava flows or ash clouds. They are measured in water displacement. They are measured in tsunami modelling. According to peer-reviewed work, a significant flank collapse on Marsili could send a tsunami racing toward the Aeolian Islands in roughly 10 minutes. The coasts of Calabria and Sicily, with their towns and harbours and beaches, in roughly 20. That is not a forecast you can run from. That is a forecast you barely have time to read before the water starts rising. And the kicker, the part that should make every coastal planner in southern Italy lose sleep, is that this scenario does not require a felt earthquake. There is no seismic alarm. There is no rumbling that gets the dogs barking before it gets bad. The volcano can fail structurally, gravitationally on its own internal timetable, and the first thing the surface will know about it is a wave. So this is the real story. Not a tiny tremor, not a beached fish, not a viral omen. The real story is that Europe has a hidden giant under its premier vacation sea, and the conventional warning systems we depend on for tsunamis are essentially deaf to one of its plausible failure modes. The earthquake we started with, that was not the threat, that was the spotlight. It pointed us, by pure coincidence, toward the thing we should have been paying attention to all along. So let's go down, let's go 3,000 meters down, and let's actually look at what is sitting under that calm blue surface. Part 6. Anatomy of Marsili. To wrap your head around Marsili, you need to abandon the picture of a volcano you carry in your head. Forget Mount Fuji. Forget the cone with the smoking summit and the postcard symmetry. Marsili is not that. Marsili is a long, sprawling ridge, roughly 70 kilometers from end to end, and roughly 30 kilometers across at its widest. From its base on the floor of the Tyrrhenian Basin to its summit, it rises about 3,000 meters, 3 vertical kilometers, the same scale as the great mountain ranges that humans have spent centuries climbing and writing books about. If you took Marsili out of the water and dropped it onto continental Europe, it would dominate the horizon. People would stop their cars to photograph it. Tourists would queue at base camps. There would be merchandise, postcards, summit certificates. Instead, it sits underwater in a body of sea most travellers consider gentle and forgiving, and almost nobody, including a lot of Italians, has any idea it exists. Now here is the second thing about Marsili that most people don't realise. It is not a single volcano. It is a volcanic ridge system, a stretched out structure with more than 80 distinct eruptive centres along its length. 80. Imagine an enormous welt on the seafloor with vents pockmarking the entire top of it, each one a potential mouth for magma to rise. That is what we are dealing with. Not a single peak with a single crater, but a whole fleet of openings spread across the spine of the ridge. How does something like this even form? It sits in what is called a back-arc basin. Imagine the Ionian plate descending into the mantle beneath Calabria. As that slab goes down, the overlying region gets stretched, like dough being pulled apart from underneath. That stretching thins the crust, pulls it open, and lets magma rise into the gap. The Tyrrhenian Sea is, in many ways, a back-arc basin in the middle of forming, and Marsili is the largest construction project that the Earth has built inside it. The internal complexity of this system is enormous. Hydrothermal systems crisscross the seamount, where seawater seeps down through cracks, gets heated by the hot rock below, picks up dissolved minerals and gases, and rises back up. Some of those plumes have been mapped by research vessels, registering as warm, chemical-rich columns above active vents. Degassing is constant in places, with carbon dioxide, hydrogen sulfide and other volcanic gases bubbling out into the seawater above. The fluids moving through this thing are not theoretical, they are real, measurable, ongoing. And yet from above, none of this is visible. The sea hides everything. The sun glints off the surface. The ferry from Naples to Palermo runs on schedule. Beneath the keel of that ferry, 80 volcanic centres murmur away in the dark on a structure taller than peaks in the Alps. Active, officially classified as active. Not extinct, not dormant in the boring textbook sense. Active. That word is doing a lot of work in this story, and once you actually understand what active means in the context of an underwater volcano this size, you cannot quite look at the Mediterranean the same way again. Part 7. Why it was ignored. So how is it possible that the largest active volcano in Europe is not a household name? How did this structure escape the public imagination for so long? The answer is partly technological, partly historical, and partly a quirk of human psychology. For most of the 20th century, the assumption about Marsili was that it was inactive, that it was a relic, that it had built itself up some long time ago, gone quiet, and was now just a big lump on the seafloor with no real bearing on modern hazard. There was no compelling reason to think otherwise. We didn't have detailed bathymetric maps. We didn't have submersibles dropping down to the summit and taking samples. We didn't even have a clear picture of the seamount's geometry. It was a label on a chart, not a personality in our minds. That assumption started to shift slowly, then suddenly. Submarine sampling campaigns brought up rocks that, when analysed, showed the chemical fingerprints of relatively young volcanism. TIFRA analysis, the study of volcanic ash layers, pulled cores from the surrounding seafloor that contained material consistent with eruptions inside the last few thousand years. In geological terms, that is yesterday. We are not talking about a volcano that last erupted in the age of the dinosaurs. We're talking about a volcano that has erupted within the time span of recorded human civilization in the Mediterranean. The Romans were already building roads when this thing was potentially still venting. The Smithsonian Global Volcanism Program eventually catalogued Marsili in its database with a status that reflects this. Active. Not historically erupted in confirmed observed terms, but active in the sense that the evidence points to recent activity and ongoing potential. That is a meaningful designation, and it puts Marsili in the same broad category as volcanoes that we routinely watch with concern. Despite that, monitoring of Marsili has remained underfunded compared to its onshore cousins. Etna has a massive monitoring infrastructure. Vesuvius, sitting next to Naples, has eyes on it from every angle, with seismometers, gas sensors, deformation monitors, and round-the-clock human observation. Stromboli has cameras pointed at its vents. Marsili has, comparatively, a handful of seafloor instruments and occasional research expeditions. Some of that is improving. Italian research institutions have made real progress in placing autonomous underwater observatories in the Tyrrhenian. But compared to the famous volcanoes you can drive to and look at, Marsili is in the equivalent of a black box. This delayed recognition matters, because the public risk perception of a volcano is shaped, at least partly, by how visible it is. You can see Vesuvius from the streets of Naples. You can see Etna from a bar in Catania. You drive past them. They live in postcards and movies and travel guides. Marsili lives in PDF papers and academic conferences, which means that, to the average resident of southern Italy, or the average tourist on a beach in Sicily, the most dangerous volcano in their lives might as well be a rumour. That asymmetry between geological reality and public awareness. That is the gap this entire video is trying to close, because the longer that gap stays open, the longer Marsili gets to keep doing whatever it is doing without anyone really paying attention. And if there is a single recurring lesson in volcanology, it is that the volcanoes you forget about tend to be the ones that get the last word. Part 8. The Eruption Misconception. There is a comforting assumption that a lot of people have when they first hear about an underwater volcano. The assumption goes something like this. Sure, it is a volcano, but it is under 3 kilometers of water. The water is heavy, the pressure must crush any explosion. So even if it erupts, it will be a quiet thing, a slow ooze of lava, harmless from above. The sea will absorb everything. That assumption is wrong, and it is wrong in interesting ways. Yes, water pressure does suppress some eruption styles. Yes, deep submarine eruptions are different from the violent atmospheric explosions you see on television footage of mountains like St. Helens. But pressure alone does not turn a volcano into a polite, gentle event. What governs eruption style is the balance between pressure and gas content. If the magma is rich enough in dissolved gases, those gases want to come out of solution, and they can do so explosively even at significant depth. We have direct evidence of explosive eruptions from submarine volcanoes. Ash deposits have been pulled from cores in many parts of the world's oceans, deposits whose grain sizes and shapes show that the magma fragmented violently as it erupted. The water didn't smother the explosion. The explosion happened anyway, just under a roof of seawater. We have documented submarine eruptions in places like the Tonga Arc and elsewhere that send plumes high enough to break the surface and inject material into the atmosphere. For Marsili specifically, geological work has identified evidence consistent with explosive activity in its past. Fragments of pumice and ash that imply gas-driven eruptions, not just quiet, effusive lava flows. Combined with its size and its complexity, the 80-plus eruptive centres, the ridge geometry, the back-arc tectonic context, it is reasonable to assume that the eruption styles available to Marsili over geological time include the dramatic ones, not just the gentle ones. Now, here is the surprising twist. Even though we should not dismiss the possibility of an eruption, the eruption itself is not actually the primary hazard most experts focus on for Marsili. An eruption from somewhere on its summit would be alarming, but the seafloor would absorb a lot of that energy, the sea would muffle the surface effects, and depending on the exact location and intensity, the effect on coastal life might be dramatic but not necessarily catastrophic in the worst sense. The thing that keeps people awake, the thing that has driven a lot of the recent modelling work, is something else entirely. It is the structural stability of the seamount itself. The question of whether one of those flanks, those long sloped sides of the ridge, is stable enough to stay where it is. or whether, under the right combination of factors, a chunk of it could let go and slide. Because if that happens, you don't need a classic eruption. You don't need pyroclastic flows or ash plumes or lava fountains. You just need a piece of the mountain to move. And the mountain is so large and the flanks are so tall that the consequences of even a moderate slide are written in numbers that make you stop reading and check that you understood the units. So eruption is not nothing, but eruption is not the headline. The headline is what happens when an underwater giant starts losing pieces of itself. Part 8. Hydrothermal weakening. To understand why those flanks might not be as stable as they look, you have to understand a slow, invisible process called hydrothermal alteration. It sounds like a textbook term. It is, but the basic idea is wonderfully tangible if you let it sink in. Picture this. Seawater seeps down into cracks in the volcano's hot rock. As it descends, it heats up. As it heats up, it becomes a chemically aggressive fluid. It picks apart the minerals in the rock, dissolving some, depositing others, transforming hard volcanic basalts into softer, more crumbly minerals. Over enough time, what was once a tough piece of igneous rock can be partially converted into something that behaves a lot more like clay. Same shape on the outside, mechanically very different on the inside. Now imagine that this process is going on slowly, continuously for thousands or tens of thousands of years across a huge volcano. You don't get this transformation everywhere uniformly. You get it concentrated along fluid pathways, fractures, fault zones, areas where hot fluids have been moving up through the structure. So you end up with a body that is mostly strong rock, threaded with weaker zones where the rock has been chemically chewed up. If this were just an academic curiosity, fine, but there is a direct mechanical consequence. Those altered weaker zones become potential failure surfaces, slip planes, places where, under enough stress, the rock above can shear off the rock below and start to move. And on a volcano with steep flanks and a height of 3 vertical kilometers, those potential slip planes are a really big deal. Volcanologists have documented this kind of pre-existing weakening on volcanoes around the world. Researchers have studied how hydrothermal systems progressively undermine the integrity of subaerial volcanoes, the ones we can walk on, and they have found that this kind of internal decay is one of the recurring contributors to flank collapses recorded in the geological record. Mount St. Helens had altered material on its bulging flank in the days before its famous lateral blast. Other volcanoes around the planet have shed enormous landslides into surrounding terrain, often along zones that had been weakened by long-term fluid alteration. Now apply that picture to Marsili. We have a volcano with active hydrothermal venting. We have evidence of fluid pathways through the structure. We have a system that has been doing this work for a long time. And we have a geometry, the long ridge, the steep slopes, the towering height, that is almost designed to convert internal weakness into gravitational hazard, given enough time and the right trigger. The frustrating part, scientifically, is that we cannot easily see this weakening. We cannot drill the entire seamount. We cannot do an MRI on a 3-kilometer tall underwater ridge. We have to infer the state of its insides from indirect measurements: gravity, magnetics, seismic profiles, occasional rock samples, and our resolution is limited. So the honest answer to how weak is Marsili right now is that we don't fully know. We know the process is happening, we don't know the exact distribution. That uncertainty is uncomfortable, but uncertainty is not the same as safety. A volcano that might be quietly weakening from the inside on a timescale we cannot precisely track is not the same as a volcano we can confidently call stable. It is a volcano whose flanks deserve respect even when nothing dramatic is happening at the surface, and a flank that is weaker than it looks is a flank waiting for the right shove. So what could that shove actually be? Part 9. The flank instability problem. A flank collapse is, mechanically, almost stupidly simple. A piece of a volcano breaks loose and slides under gravity. The size can range from modest, a chunk of slope a few hundred meters across, to massive, a slab of mountain large enough to redraw a coastline. The geological record on land and sea is full of examples. Hawaii has shed enormous chunks into the Pacific over its lifetime, the Canary Islands have similar histories, and the evidence sits in deposits sprawled across the seafloor for tens of kilometers downstream. For Marsili specifically, the geometry is suggestive. You have a long, narrow ridge with steep flanks rising thousands of meters above the surrounding basin. On any object that tall and that narrow, the sides are inherently somewhat exposed to gravity. The taller and steeper they are, the more energy is, in a sense, stored as potential hazard. You don't need a complex mechanism, you need a region of weakness, an excess of steepness, and a trigger. Has Marsili already had collapses in its past? The honest answer is that the evidence is suggestive rather than conclusive. The seafloor around large submarine volcanoes can preserve the signatures of past slope failures, chaotic deposits, scarp features, characteristic morphologies. Some surveys around Marsili have identified features that look consistent with past mass-wasting events, indications that pieces of this thing have come down before. But the records aren't as clean as they would be on land, because submarine sediments accumulate over and around any old failure deposit, smoothing the picture, blurring the timing. Sediment build-up itself is part of the story. As material accumulates on and around the flanks over time, it adds weight. It can change pore pressures in the underlying rock. It can subtly alter the load on already weakened zones. Combine that with hydrothermal alteration eating away at the inside, and you have a system whose stability margin is gradually shrinking even when nothing dramatic is happening from above. The triggering mechanisms for an actual collapse can be varied. A nearby earthquake, a magma intrusion that pushes rock outward, a change in fluid pressure inside an altered zone. Sometimes none of the above. Sometimes the system simply reaches its limit on its own internal schedule, with no obvious external nudge. That last possibility is the one that haunts hazard assessments, because it implies you can have a major collapse with essentially no immediate warning. This is the part of the story where I want to be careful. I'm not telling you this is going to happen tomorrow. I'm not telling you to cancel a Mediterranean cruise. The probability of a major flank collapse on Marsili in any given year is, by all reasonable estimates, low. What I am telling you is that the consequences, if it does happen, are large, and the warning we would get is short. That is the asymmetry that defines this entire investigation. Because here is the part most people miss when they imagine volcanic disaster. You don't need an eruption to get a tsunami from a volcano like Marsili. You just need a piece of the mountain to move. The water above doesn't care whether the rock is glowing hot or stone cold. It only cares that something pushed it, and how hard. So how exactly does a sliding chunk of seafloor turn into a wall of water at your favourite holiday beach? Part 10. The mechanism. Most people, when they think about tsunamis, picture the seismic kind, a big subduction earthquake offshore. The seafloor jolts upward, the water above gets shoved upward with it. That displaced water radiates outward as long, low waves, travelling at the speed of a jetliner across the open ocean and eventually piling up into something monstrous when it reaches a coast. That is the mechanism behind the great Pacific tsunamis of recent decades. That is the mental movie when you hear the word. The tsunamis you can get from a flank collapse are mechanically a different animal. They are landslide tsunamis. Instead of a wide swath of seafloor flexing, you get a localized violent displacement. A huge chunk of rock and sediment tears loose and accelerates down the slope of the volcano. As it moves, it pushes the water in front of it like a hand swinging through a bathtub. The water has to go somewhere. It goes up and it goes outward in a wave that radiates from the point of failure. There are real-world analogue events that show this mechanism is not theoretical. The Lituya Bay event in 1958, when a rock slide into a confined Alaskan inlet generated an absolutely monstrous wave that scoured trees off mountainsides at heights you can barely believe. The collapse generated tsunamis from volcanic islands like Anak Krakatau in 2018, where a flank failure on a relatively modest underwater volcano produced a wave that killed hundreds of people on Indonesian coasts, with essentially no warning, because there had been no triggering earthquake of the kind that automated systems are designed to detect. The crucial difference between a seismic tsunami and a landslide tsunami is the speed of onset and the local intensity. Seismic tsunamis often have hours of travel time across an ocean. They can be enormous when they hit a far coast, but the regions near the source often experience them within a few minutes, similar in some ways to landslide tsunamis. The signature of a landslide tsunami, though, is that the energy is concentrated, the source is localized, and the timing is brutally short for nearby coastlines. There is no friendly hour for civil defense to mobilize. There is, in many scenarios, barely any time at all. There is a useful analogy here, even if it is imperfect. Imagine a bathtub. Imagine you push your hand into one end hard. The water doesn't politely rise on the far side. It sloshes, it reflects, it stacks against the walls. A confined basin behaves like that bathtub at scale. The Tyrrhenian Sea, while not exactly small, is geographically constrained, surrounded by Italy, Sicily, Sardinia, and the various islands. A wave generated inside it doesn't dissipate over a clean ocean expanse. It bounces, it focuses, it amplifies in some places and weakens in others, depending on coastline shapes and seafloor topography. Now picture this happening at Marsili. A flank gives way somewhere on its long ridge. A huge volume of rock and sediment, accelerated by gravity, pushes water aside as it slides toward the basin floor. The wave generated by that displacement is not random. It is largely determined by the size, speed, and direction of the failure. Modelling work by Italian researchers has tried to map out the kinds of waves you could expect for different scenarios. Small failures, medium failures, large failures. The numbers vary, but the qualitative picture is consistent. Significant waves, reaching nearby shores in minutes, not hours. That number, minutes, is the one I want lodged in your mind, because everything we're about to talk about flows from that single brutal fact. Part 11. Timing reality. Let's actually look at the timing modelled for a Marsili tsunami, because this is where the abstract becomes immediate. The Aeolian Islands, Stromboli, Lipari, Volcano, Salina, the rest, are sitting close to the seamount in geographic terms. According to peer-reviewed scenarios, a wave from a significant Marsili flank failure could reach these islands in roughly 10 minutes. The coastlines of Calabria and Sicily, with their towns, harbours, hotels and beaches, in roughly 20 minutes. To appreciate what those numbers mean, let me put them next to a famous comparison. The 2011 Tohoku earthquake and tsunami in Japan was one of the most studied tsunami events in modern history. Even in that case, where the tsunami was generated by a massive offshore earthquake that was clearly felt on land, the warning windows for the closest Japanese coastlines were short. People had minutes to tens of minutes to evacuate. Many escaped. Many did not. The infrastructure of warning systems, sirens, vertical evacuation, public education, all of it had been built specifically because Japan had learned that lesson the hard way over centuries. In a Marsili-style scenario, the warning window is at the brutal end of that range, with the additional brutal feature that there might be no triggering earthquake at all, no felt jolt, no reason for someone walking on a beach in Lipari to think, "That was strange, I should head uphill." The first signal that something was wrong might be the water itself, doing something it shouldn't. The wave propagation speed in deep water is fast, hundreds of kilometers per hour fast. Once a wave has been generated near Marsili, the clock starts running, and the clock runs in the wave's favour. You can model it, you can map it, you can publish papers about it. None of that buys you any extra seconds in the actual event. Coastal vulnerability in this region is not abstract. The Aeolians are popular tourist destinations. The Calabrian and Sicilian coasts are dotted with towns, marinas, agricultural lowlands, ferry routes and infrastructure. Many of these places are oriented toward the sea. That is the entire point of being a coastal town, which means they are also exposed to the sea, in a way that becomes a liability when the sea decides to come in faster than expected. Compare this with the kind of warning we have for ocean-scale events. When a tsunami is generated in, say, the Pacific, even regions thousands of kilometers from the source typically get warning lead times measured in hours. That is enough time for sirens, for organised evacuations, for people to get phone alerts and act on them. The Tyrrhenian scenario is not in that league of warning time. It is not even close, and human response limits are what they are. Even with perfect detection, perfect alerting, and perfect public education, the gap between a notification arriving on a phone and a person physically getting to safe ground takes minutes by itself. If the entire warning to impact window is 10 or 20 minutes, you're operating at the very edge of what is biologically and logistically possible for a population to do. You can save many lives with good systems. You will not save everyone. So now we have a realistic picture of the timing, and the next, and possibly worst part of the story is what those systems are actually designed to detect, and what they are not. Part 12. No precursor problem. Modern tsunami warning systems are built around the assumption of a triggering earthquake. The logic is simple. The biggest tsunami producers in human history have been large submarine earthquakes. So you put seismometers everywhere. You watch for a big jolt offshore. You estimate its size, depth and location in real time. You combine that with seafloor pressure sensors, with tide gauges, with deep ocean buoys. If the system thinks a tsunami is plausible, it issues an alert and starts the timers. This system saves lives. It works. It worked, with significant limitations even for the 2011 Tohoku event. It works for the kind of tsunami that announces itself in the seismic record before it announces itself at the shore. A Marsili flank collapse can, in the worst-case scenarios, simply bypass that system. If the failure occurs without a substantial earthquake, just a slope giving way along an already weakened zone, there is no big seismic signal for the conventional alert system to catch. The instruments are listening for one specific type of cue, and the event speaks a different language. By the time the wave registers on coastal tide gauges, the wave is already at or near the shore. This is what we mean when we talk about a silent failure scenario. Not silent in the sense that the volcano is invisible from satellites, although it is. Silent in the sense that the mechanism of disaster does not pull the alarm cord on the way out, it just unfolds. Detection limitations make this worse. We do not have the same density of seafloor monitoring on Marsili that we have on, say, an active onshore volcano under heavy observation. You cannot easily notice a slow, creeping deformation on an underwater flank without dedicated instruments deployed in the right places, and there is real research effort going into improving exactly that capability. But until those systems mature, there are gaps. There are things the current network would simply not catch in time to make a difference. That gap creates a false sense of security, and the false sense of security is, in some ways, the most dangerous thing of all. People living along the Tyrrhenian coast, planning beach holidays, building homes, expanding harbours, are operating inside a mental model that says, if something terrible were going to happen, we would know in advance. Sirens would go off. Alerts would buzz on phones. The news would have been talking about it for days. That model is reasonable for many natural hazards. It is not robust for the specific Marsili-style scenario. A useful comparison is the Cascadia subduction zone in the Pacific Northwest of North America. There, the tsunami warning window for the closest coastal communities is famously short, minutes to tens of minutes, and the regional emergency planning has been gradually built around that fact. People drill, people learn the routes, people understand viscerally that if you feel the ground shake hard for a long time, you go to high ground without waiting for any instructions. Whether that planning is enough in practice is another story, but at least the framing is honest. For Marsili, the equivalent honest framing has not been culturally absorbed. Most people who would be affected by a worst-case scenario don't know the volcano exists, let alone that they should think about what to do if the sea does something strange one afternoon. That is the gap this video is trying, in some small way, to start to close, because the zero warning possibility doesn't go away just because we choose not to look at it. It just sits there, patient, indifferent, factored into nobody's plans. So even if a wave is generated, you might wonder, surely the open sea will absorb a lot of it. Surely the basin will spread the energy out. Let's go look at that. Part 13. Basin Geometry. The Tyrrhenian Sea is, in basin terms, a particular kind of beast. It is a roughly enclosed body of water. To its east lies the Italian peninsula, to its west Sardinia, to its south Sicily and the long arc of the Aeolian Islands. To the north, it narrows toward the Ligurian Sea. It is large enough to be impressive on a map, but small enough that a wave generated near its centre cannot just dissipate forever into open ocean. It has to deal with coastlines. Wave reflection in a basin like this is non-trivial. A pulse of water generated near Marsili radiates outward, bumps into coastlines, reflects, interacts with the next pulse, and starts producing complex patterns. Some places end up with waves that arrive smaller than expected. Other places, depending on coastline orientation, seafloor shape, and bay geometry, end up with waves that are dramatically larger than the open water amplitude would suggest. This is called amplification, and it is one of the most important things to know about how local tsunamis behave. You see this in coastal focusing zones. Bays that act like funnels can take a modest wave and concentrate it. Headlands and submarine ridges can refract waves towards specific stretches of coast. Two parts of a coastline that look superficially similar on a map can experience radically different conditions during the same event, because the seafloor in front of them shapes the wave differently. This is why tsunami modelling is not just about the source. It's about the geometry of every coastline the wave touches. Compare this to the open ocean behaviour of a Pacific tsunami. There, a wave can travel thousands of kilometres, slowly losing energy, before piling up against a distant coast. The distance gives it time to spread out. The depth gives it room to behave. In the Tyrrhenian, those luxuries are reduced. You have a confined volume, a complex coastline, and a source that is not at the centre of a vast ocean, but right in the middle of a basin surrounded by populated land. Resonance is another factor. Enclosed and semi-enclosed bodies of water can have natural oscillation periods, ways the water likes to slosh back and forth. If a tsunami's frequency content overlaps with those modes, you can get amplification effects that persist for hours after the initial wave, with multiple peaks and troughs continuing to threaten coastlines well beyond the first impact. This is part of why post-tsunami warnings often emphasise that the first wave is not always the largest, and that staying away from the coast for an extended period is not paranoia, it is sound advice. So the picture is not the open sea will swallow the wave and we will be fine. The picture is more like a confined basin will reshape the wave in ways that are hard to predict precisely, focusing it on some communities and sparing others, with effects that can ripple through the basin for hours. The best modelling we have can give us probabilistic ranges. It cannot tell you which town in particular gets hit hardest until the event itself is unfolding. That uncertainty is its own kind of hazard. It means you cannot say this town is safe. You can only say this region of coastline is exposed, and within that region, individual fates depend on details that we cannot fully resolve in advance. Which brings us to the question that anyone honest about this scenario eventually has to ask. How big is big? When we talk about a flank collapse on Marsili, what range of magnitudes are we actually talking about? Part 14. Scenario Scaling. Flank collapse scenarios on a volcano like Marsili are not a single thing. They live on a spectrum. At the low end you have small failures, a chunk of slope a few hundred metres across, or a localised landslide along one zone of weakness. Events like that are not negligible. They could still produce locally significant waves, but the consequences would be regional and probably manageable in the same general category as some other historical local tsunamis. At the medium end, you have failures involving cubic kilometres of material, a substantial section of a flank sliding as a more or less coherent mass into the surrounding basin. These are the scenarios that produce the kind of timing and amplitude estimates that show up in the headline-grabbing modelling papers. Aeolian Islands in roughly 10 minutes, Calabria and Sicily in roughly 20, with waves that could pose significant hazard to coastal communities in those areas. At the high end, you have catastrophic failures, large fractions of an entire flank giving way at once, generating waves whose effects on the basin would be regionally devastating. These scenarios are at the lower probability end of the spectrum, but they are not impossible. They are what the geological record shows have happened at other volcanoes around the world, given enough time. They are not unique to Marsili. They are part of how this category of mountain ages. Energy scaling matters here. The energy released in a slope failure depends on how much mass moves, how far it falls, and how fast it accelerates. Small differences in volume can produce big differences in wave generation. The result is that the uncertainty range on tsunami amplitudes is not narrow, it is wide. Different reasonable assumptions about failure size produce different reasonable estimates about wave height and run-up, and the resulting hazard maps reflect that. When you combine probability with impact, you get into the territory that risk analysts call low-frequency, high-impact events. The probability of a major Marsili-related tsunami in any given year is small. The impact, if it occurs, would be substantial. Multiplied across decades and centuries, the cumulative risk is non-trivial. This is the same category as major earthquakes in many regions, large volcanic eruptions, asteroid strikes, and other phenomena where most of the time, in any given year, nothing happens. But where the consequences of the rare year that does see something happen are severe enough to justify ongoing attention. Misconceptions about this category are common. People often interpret low probability as essentially zero. They make decisions about coastal infrastructure, real estate, evacuation planning, and personal travel as if the worst-case scenario was so unlikely as to be ignorable. That works fine for many years, even decades. It does not work over timescales long enough for the rare event to occur, and the rare event, when it comes, does not care how many uneventful decades preceded it. This is the real takeaway of scenario scaling. Low probability does not mean no risk. Wide uncertainty does not mean we can choose the comfortable end of the range. The honest framing is, here is a hazard that is real, that is rare, that is uncertain, and that is consequential. Treat it accordingly. Build awareness, improve monitoring, plan evacuation routes, and pay attention to the system as a whole, because the system is always doing something, even when no headlines are being generated. So if we zoom out from Marsili specifically, what is the larger system that produces a giant like this in the first place? Part 15. The Calabrian Arc Machine. To really understand Marsili, you have to understand the engine that built it. That engine is called the Calabrian Arc, and it is one of the more complex pieces of plate tectonics in the Mediterranean. Picture the boot of Italy. The toe of that boot is Calabria. Just offshore from Calabria, the seafloor plunges, taking a piece of oceanic lithosphere, the Ionian plate, down into the mantle. That descent is not slow on geological timescales. It is one of the more active subduction systems in the region, even if it is small by global standards. As that slab descends, several things happen at once. Water, as we mentioned earlier, is squeezed out and triggers melting in the mantle wedge above. That melt rises and produces the volcanoes of southern Italy, including Etna and the Aeolians and the wider arc of activity. Meanwhile, behind the arc, which means in the direction away from where the plate is going down, the overlying lithosphere is being stretched. That stretching is what opens up the back arc basin. That basin is the Tyrrhenian Sea, and inside that opening basin, magma rises into the new crust being formed and builds structures like Marsili. So Marsili is not a random volcano dropped onto the seafloor. It is a direct expression of the back arc extension, a place where the Earth is, in geologic terms, currently constructing new ocean floor. The back arc setting is fundamentally different from the front arc setting, where Etna and Stromboli sit. It produces different magmas, different morphologies, different volcanic styles, and it is part of the reason Marsili looks so unusual, that long ridge with 80+ eruptive centres, rather than the classic single cone shape we associate with subduction zone volcanoes. Regional stress fields in the Calabrian Arc are not constant. They evolve. The slab is not descending at a perfectly steady rate. Different parts of the system can lock and unlock on different timescales. Big earthquakes have happened in this region in historical time, including events in Calabria and Messina, that caused tremendous loss of life. The seismicity here is real, ongoing, and connected to the same machinery that ultimately drives the volcanism. What this means is that Marsili is not an isolated risk. It is one node in a regional dynamic environment that includes earthquakes, volcanoes, slow tectonic movements, and the long-term evolution of the Tyrrhenian Basin itself. To think clearly about Marsili, you have to think about it as embedded in this larger system, not as a standalone curiosity. The system is the thing that loads Marsili over time. The system is the thing that, eventually, will generate whatever Marsili does next. The timescales here matter. This is not a system that changes its behaviour in days or weeks. Plate motions are measured in centimetres per year. The processes that build, weaken, and eventually fail volcanoes in this setting unfold over centuries to tens of thousands of years, which means that, on any given day, including today, the most likely outcome is nothing changes. The system keeps doing what it does. The boring answer is correct most of the time, but every now and then, the system stops being boring, and when it does, it tends to do so in ways that involve more than one volcano at a time. Part 16. Linked Volcano Network. Marsili does not live in a vacuum. The Tyrrhenian system includes some of the most famous volcanic features on the planet. Stromboli, the constantly burping island volcano, the Campi Flegrei caldera near Naples, an enormous restless caldera that has produced some of the largest eruptions in European prehistory. Etna on the other side of the Strait of Messina, technically not a back arc volcano, but absolutely linked into the same regional subduction architecture. Each of these has its own personality, its own monitoring history, its own news cycle. Stromboli does its low-level Strombolian activity and occasionally throws a paroxysm that makes international headlines. Campi Flegrei has been in a phase of unrest with ongoing uplift and seismicity that has justifiably drawn intense scientific attention. Etna does what Etna always does. which is mostly nothing dramatic and occasionally something spectacular. What links them is shared origin. They are all expressions of the same plate tectonic situation. They all draw, to varying degrees, on magmas produced by the descent of that Ionian slab. They all sit inside the same broad regional stress field, none of which means they erupt in synchrony. They mostly do not, but it does mean that significant changes in the deep plumbing of the region can, in principle, influence multiple parts of the network at once. I am not going to take you down a deep rabbit hole on each of these individually, because that is not the spine of this story. The spine of this story is Marsili. Marsili is unique among these systems because it is hidden, because it is structurally a different kind of volcano, and because the worst-case scenario it presents, a tsunami without a felt earthquake, is something that no other volcano in this network is positioned to generate at the same scale. So treat Stromboli and Campi Flegrei and Etna as siblings, all members of the same Mediterranean volcanic family. They share a household, they share parents in the form of plate tectonics. But the one we are circling back to is the sibling who is hardest to keep an eye on, because they are always in a different room with the door closed. Marsili is that sibling. And what makes Marsili dangerous is precisely the combination of being part of an active family and being the one nobody is watching closely enough. Part 17. Stress Transfer Hypothesis. Here is where we get into a more speculative but scientifically interesting idea. Earthquakes in the deeper parts of subduction zones can, in some cases, redistribute stress in ways that influence overlying systems. The deep rupture changes the load on certain rock volumes. That changed load can subtly shift the conditions in which fluids move, in which magmas accumulate, in which other faults sit closer to or further from failure. The concept is called stress transfer, and it is a well-established idea in seismology generally. When a major earthquake happens, scientists often calculate how the stress on neighbouring faults has changed, looking for which ones got loaded toward future failure and which ones got unloaded. It is a useful analytic framework. The question is whether the same logic applies in a meaningful way between deep slab seismicity and shallow volcanic systems on a given timescale. The honest answer is, it depends. Some research suggests that, over long timescales, deep events in subduction zones may correlate with changes in the behaviour of overlying volcanoes. Other research is more cautious, pointing out that volcanoes have their own internal clocks, and that pulling out a clean signal of slab influence from the noise of normal volcanic behaviour is methodologically difficult. The literature is mixed. The mechanisms are plausible but not nailed down. For Marsili specifically, you can construct a chain of logic that goes from a deep slab earthquake to changes in mantle stress, to changes in magma generation rates, to long-term evolution of the volcanic system. Each link in that chain is physically plausible. None of those links, on the basis of a single small earthquake, is likely to translate into a near-term consequence at the surface. The system has too much inertia for one little tremor to jolt it into a different state. What you can argue is that, over many such tremors and many years, the cumulative input shapes how the system evolves. So when I tell you that this earthquake under Marsili is not a near-term trigger, I am not dismissing the science, I am respecting it. The science says there is no confirmed mechanism by which a single magnitude 2.7 event at 96 kilometers depth produces a flank collapse next week. That is a defensible statement. It is also true that the deep system is, in a slow, cumulative sense, part of what determines Marsili's long-term behaviour. This nuance is important because the loud parts of the internet are not interested in nuance. They want this earthquake to be the omen, the smoking gun, the I told you so. The actual scientific picture is less satisfying. The earthquake is part of a system. The system is real. The system is active. And the most honest thing we can say is that we are still, decades after starting to study Marsili in earnest, learning how the pieces actually fit together. The healthy response to that uncertainty is not panic, and it is not dismissal. It is sustained attention. And the part of the system that benefits most from sustained attention is exactly the part we have been talking about. The hidden, structurally complex, hydrothermally active mountain whose flanks define the worst-case scenario for the entire region. Part 18. Etna's submarine extension. There is one more piece of context worth mentioning briefly, because it reinforces the central pattern. Etna does not end at the coastline. Its eastern flank extends offshore sliding very slowly seaward in a way that has been measured directly with seafloor instruments. Researchers have observed centimetres per year movement of the submarine flank of Etna into the Ionian Sea. That movement is ongoing, it is documented. It is, in a sense, a tiny landslide playing out in slow motion. The hazard implications of that creeping flank are an active area of research. If part of Etna's submarine flank were to fail more rapidly, there would be tsunami implications for nearby coasts, separate from any volcanic eruption. This is the same general category of hazard we have been discussing for Marsili, just on a different scale and at a different volcano. It is a reminder that submarine flank instability is not a hypothetical worry invented to make Marsili sound scary. It is a recognised, documented phenomenon at multiple volcanoes in this very region. This regional pattern matters for our central thread. When you see slow submarine creep at Etna, and you also know there is a hidden 3,000 metre tall ridge called Marsili in the same broader system, you understand that we are dealing with a setting where flank stability is a real, recurring theme. Marsili is, in some ways, the most extreme expression of that theme, the largest, the deepest, the least visible. The Etna submarine flank is a smaller, better monitored cousin. Different volcanoes, same family of concern, and the broader lesson is the one that keeps surfacing in this story. The Mediterranean is calmer in our imagination than it is in geology. Underneath the postcards, structures are moving, eroding, bulging, occasionally letting go. Most of the time, in tiny amounts. Once in a great while, in larger amounts, with consequences that arrive faster than warnings. Part 19, Multi-System Activation Question. So here is the question that anyone watching this story carefully has to grapple with. Are these clustered signals, a deep tremor under Marsili, a moderately deep tremor west of Etna, perhaps activity at Stromboli or unrest at Campiflegre in the same news cycle, coincidence or pattern? Statistically, the honest answer leans toward coincidence in any given short window. Earthquakes happen in this region all the time. Volcanoes here are active continuously at low levels. If you set a wide enough net for any given week, you will pull up multiple events that, if you wanted to, you could weave into a narrative of regional activation. That is exactly the kind of trap that pattern-seeking minds fall into. Background noise is mistaken for signal because the signals you actually want are rare and the noise is constant. There is also a real concept in the literature, though, called multi-system activation, or sometimes synchronized unrest or coupled volcanic behavior. The idea is that there are circumstances under which multiple systems in the same regional context show changes at roughly the same time, due to shared driving processes. It is an active area of research. The evidence is not conclusive in many specific cases, but it is not zero either. There are statistical hints that volcanoes can cluster their activity in ways that exceed what you would expect from pure chance on certain timescales. For our particular moment, the right framing is cautious. We do not currently have strong scientific evidence that the Calabrian arc is undergoing a system-wide activation phase right now. We do have evidence of low-level activity at multiple nodes, which is more or less normal for a region this dynamic. We do have specific researchers continuing to study how the various pieces interact and influence each other. None of that adds up to, the system is about to do something dramatic this week. What it does add up to is, the system is real, the connections between its parts are real, and Marsili is one of those parts. When you pull on the thread of any one node, a small earthquake, a fish on a beach, a swarm at Etna, you eventually end up holding a piece of the same regional fabric. And the part of that fabric that is most under-monitored, most invisible and most consequential in worst-case scenarios is, again, the seamount we have been circling. The cluster, in other words, is not what we should be paying attention to. The cluster is a flashlight. The thing it is illuminating is what matters. And what it is illuminating is the gap between visible signals and invisible structure. So now let's actually examine the visible signals more closely, because the public conversation is about to be dominated by one of them in particular. Part 20. The Oarfish myth tested. Let's go back to the doomsday fish, because it is going to be the part of this story that the algorithm wants you to remember. The viral images, the folklore, the shareable narrative. We owe it a clean look. The Grant and colleagues' study from 2019 examined oarfish strandings against earthquake records, looking for whether the famous Japanese cultural pattern actually held up under statistical scrutiny. The conclusion was essentially that no robust correlation could be established. Strandings did not cluster meaningfully before earthquakes, in a way that would let you use them as a predictor. The folklore, however emotionally resonant, was not borne out by the numbers when you ran them carefully. The reasons for strandings are mundane and varied. Sick fish drift with currents. Storms churn deep water and disturb mesopelagic species. Some individuals appear to die at depth and gradually rise as decomposition gases buoy them up. Others get caught in unusual surface currents that bring them into shallow water where they cannot survive. Across a long enough timeline, you accumulate a steady drumbeat of strandings, distributed essentially randomly with respect to earthquake activity. Sometimes a stranding precedes a quake by days or weeks, sometimes it does not. Lots of strandings happen, and nothing notable occurs at all. Anecdotal evidence is powerful. When somebody in Japan saw an oarfish, then a few weeks later an earthquake happened, the human brain locks that pair together as cause and effect. The thousands of times an oarfish appeared and nothing notable followed get filed under, "Oh, I guess that one didn't mean anything." The asymmetry of memory creates a false signal where the underlying data is essentially noise. This is not me dismissing the people who notice these things. The instinct to look for omens is ancient and in many environments has served humans well. It is the same cognitive machinery that helps you spot subtle clues in your immediate surroundings. The problem is that this machinery is not calibrated for global-scale data sets. It is calibrated for the small village of your evolutionary past, where remembering hits and ignoring misses was a survival advantage. Applied to social media, it produces conspiracies and patterns that look real and aren't. So when the oarfish in Denmark and the one in Ireland show up in the same news cycle as a tremor under Marsili, the brain wants to fuse them. The data, taken honestly, says two oceanic events that happen to overlap in time without a demonstrated mechanical link. That is not nothing emotionally, it is nothing scientifically. And while the conversation focuses on whether the fish are an omen, the actual hazard, the hidden 80-vent volcanic ridge whose flank stability is the real issue for southern Italian coasts, sits right there in the background, undiscussed, unphotographed, and unfortunately unforgettable in the way that should matter most. Part 21. The Electric Field Theory. There is a more scientific-sounding version of the omenfish story that deserves a fair hearing, because some viewers will inevitably bring it up. The theory goes that before earthquakes, stressed rock under the seafloor generates tiny electric fields. Some species, including possibly oarfish, have organs sensitive to electrical stimuli and might be disturbed by these fields, leading them to surface in unusual ways. There are real biological phenomena involving electroreception in fish. Sharks, for instance, have famously sensitive electric sense. So the framework is not nonsense at the level of biology. The problem is the gap between the theoretical framework and the evidence. Measuring the relevant electric fields in the relevant locations at the relevant times in a way that demonstrates a robust link to specific earthquakes is hard. Most of the high-confidence evidence for pre-seismic electromagnetic phenomena comes from a small number of cases that are still actively debated in the scientific community. There is no dataset that I am aware of where someone has cleanly tied oarfish surfacing behaviour to measurable seismic precursor electric fields in a way that would survive rigorous review. So the electric field idea is not crazy. It is just not currently supported. It is one of those theories that fills a narrative gap nicely without filling the corresponding empirical gap. People hear it and feel like they understand. The actual measurement systems we have in the ocean are not yet capable of definitively confirming or denying the underlying mechanism. This matters for our central thread, because every minute spent debating whether oarfish are sensing electromagnetic precursors is a minute not spent thinking about how thoroughly we can detect and respond to a flank collapse on Marsili. The electric field theory is, at best, a hypothesis about a small biological signal. The Marsili hazard is, at minimum, a documented physical scenario with well-defined consequences. The first should not crowd out the second in our mental budget. If anything, the absence of solid evidence for biological precursors reinforces, rather than weakens, the importance of the geological hazard. We do not have a magical fish that will warn us. We have instead a need for instruments, monitoring, education, and planning. Part 22. Conspiracy Layer. Inevitably, in any story like this, a conspiracy layer arrives. The narrative goes something like this. The authorities know more than they are telling us. The risk has been suppressed to protect tourism. Someone in a position of power is sitting on critical data because it would crash the housing market or empty the cruise terminals. The truth is being hidden, and by spreading the word about it on social media, ordinary people are heroically uncovering what the experts won't admit. I want to take this idea seriously, because dismissing it without engagement would feel hollow to many viewers. Distrust of institutions is a real thing in the world. It comes from real failures. There have been real cases where authorities downplayed real risks. Skepticism is not by itself irrational. In the specific case of Marsili, however, the suppression narrative does not fit the actual situation. The hazard has been openly published in peer-reviewed journals for years. The Italian National Institute of Geophysics and Volcanology has discussed the seamount. International researchers have written modelling papers about flank collapse scenarios that are freely available to anyone with an internet connection. There is no padlocked vault containing the secret of Marsili. The secret, to the extent there is one, is sitting in the open scientific literature where it has been quietly waiting for public attention. What there is instead is institutional inertia. The story is technical. It is hard to explain in a 30-second clip. It does not fit easily into a tourism brochure. It does not produce dramatic visuals because the volcano is invisible from the surface. So even though the data is openly available, it has never broken through into mass awareness in the way that a visible volcano like Vesuvius has. That is not suppression. That is communication failure, plus the constant background noise of every other thing the world is paying attention to. The conspiracy framing, ironically, gets in the way of the actual concern. By turning Marsili into a story about authorities versus citizens, it distracts from the much more useful story, which is, here is a real hazard. The science is open, you can read it, you can talk about it with your local emergency planners, you can know what to do if you see the sea behave strangely. The conspiracy framing makes you feel powerful for noticing something. The accurate framing actually empowers you to do something useful. So when you see comments under videos like this one talking about cover-ups and silenced scientists, take them with a grain of salt. The information is out there. The conversation just hasn't been loud enough yet. Loud is what we are trying to do here. Part 23. HAARP/artificial trigger claims. Briefly, because this comes up whenever any geological event makes the news, there is a class of theories that attribute earthquakes and volcanic activity to artificial causes, weapon systems aimed at the planet, atmospheric heaters being used to trigger seismicity, secret experiments in upper atmosphere physics manipulating the Earth's interior. I will be quick. The energy budgets involved in moving large pieces of the lithosphere are vastly larger than anything humans have ever generated artificially. The technologies that get cited in these theories are real research programs, with mundane and well-documented purposes related to studying the ionosphere. But they cannot do what they are accused of. A magnitude 2.7 earthquake at 96 kilometers depth is not within the reach of any artificial system that exists, and inventing one that could do it would be like inventing a flashlight that could push the moon. The physics says no. The reason this matters for our central thread is that artificial trigger theories, like the doomsday fish, root attention away from the actual geological situation. They make Marsili a piece of a fantasy, when it is in fact a piece of plate tectonics. The reality is more interesting than the conspiracy. A self-organizing planet whose continents drift, whose plates collide, whose subducting slabs build hidden volcanoes that occasionally fail in ways we are still learning to monitor. That is a remarkable story even without supervillain technology. The conspiracy version is frankly less interesting and less true. Strip away the artificial explanations, and what is left is the original grounded concern. A real volcano, a real ocean, real coasts, real timing. That is enough. Part 24. Why these narratives persist. So why do these narratives, the omen fish, the electric field, the suppression, the artificial triggers, keep showing up around stories like this? The short answer is human cognition. The longer answer is more interesting. We are wired to prefer visible signals. A fish on a beach is visible. A conspiracy theory is, in a strange way, also visible. It gives you a villain you can picture, a motive you can articulate. An invisible structural risk 3,000 meters under the water, on the other hand, is the opposite of visible. It is a shape you cannot see, doing something you cannot watch, on a timescale you cannot feel. Cognitively, that is hard to hold on to. We are also drawn to immediate causes. The fish appeared, then the earthquake happened, so the fish caused the earthquake. The officials said something, so they must be hiding something. These narratives offer immediate, satisfying explanations. The truth, that complex systems unfold over long timescales, with multiple interacting factors and significant uncertainty, is psychologically less satisfying. It does not give you a clean enemy, it does not give you a clean prophet. Media amplification cycles take all of this and dial it up. Outlets compete for attention. Attention rewards drama. The doomsday fish framing is dramatic. The careful, paragraph-long discussion of slab dehydration and back arc extension is not, at least in the algorithmic sense, so the dramatic version travels faster. The accurate version, if it reaches the audience at all, often arrives second, when the first version has already shaped the conversation. There is also a strange psychological comfort in patterns, even scary patterns. If the world is a place where omens precede disasters, then at least the world makes sense. The terrifying alternative, that disasters can come without omens, that hidden structures can fail without any visible cue, is harder to live with. The omen narrative, even when it predicts terrible things, offers a kind of meaning. The honest scientific narrative, with its uncertainty and its gaps, offers truth instead, which is colder. For our central thread, this is exactly the dynamic that keeps Marsili overlooked. The visible omen story is satisfying in a way that the invisible structural story is not. A doomsday fish makes for a great thumbnail. A back arc seamount with hydrothermally weakened flanks does not. So the public conversation gets crowded with the satisfying story, and the actual hazard sits in the corner, doing whatever it is doing on its own time. The asymmetry between what is visible and what is real, that is the heart of why these narratives persist. And that asymmetry is also exactly the structure of the actual physical hazard. Visible signals out, invisible danger in. The story we tell mirrors the geological situation more than we realise. So let's bring this all together and look squarely at the asymmetry that defines this entire story. Part 25. The visibility gap. There is a peculiar bias in how humans rank natural hazards, and it has to do with how easy something is to see. Vesuvius is famous because you can stand in Naples and look at it. The cone is right there, looming, photogenic, mythologized in art and literature for 2,000 years. It has presence. It has personality. People know it exists. Marsili has none of those advantages. There is no skyline in any city of southern Italy where Marsili appears. No tourist takes a selfie with Marsili behind them. No film opens with a sweeping aerial shot of its summit. Its summit is underwater, half a kilometre below the surface, in a stretch of sea that looks, to every passing eye, like every other patch of Mediterranean blue. From the perspective of human visual culture, Marsili effectively does not exist. Monitoring limitations follow from this. On Vesuvius you can plant seismometers all over the structure, fly drones over the crater, watch fumaroles, take temperature readings, observe ground deformation with satellite-based interferometry. On Marsili, every single one of those capabilities is harder, more expensive, or impossible. You can deploy seafloor instruments, and people are doing this, but you cannot blanket a 3-kilometre tall underwater ridge with sensors the way you can a subaerial cone. The basic tools of modern volcanic surveillance work less well when the object of surveillance is hidden under an ocean. The awareness gap mirrors the visibility gap. Public understanding of risk tracks, almost perfectly, public visual familiarity. People who live next to a visible volcano usually know it is there, know it has erupted before, and have at least some folk knowledge about what to do if it acts up. People who live next to an invisible volcano, and let's be clear, plenty of southern Italians live within the projected impact zone of a Marsili-related tsunami, generally have no idea that anything unusual is even out there. That is the visibility gap. It is the foundational asymmetry of this entire story. The most dangerous thing is the thing nobody can see. And the thing nobody can see is, partly because of that invisibility, the thing nobody is talking about, the thing nobody is planning around, the thing nobody is allocating sufficient public attention or resources to monitor at the level it deserves. If you remember nothing else from this video, remember that. The most consequential hazards are not always the most visible ones. Often they are the opposite. The hidden ones, the slow ones, The ones that don't have a profile picture are the ones that quietly accumulate the worst-case potential, while the visible ones absorb all of the public worry. Marsili is the textbook case of that asymmetry in the actual textbook of European geology. Part 26. The time gap. There is a second asymmetry that defines this story, and it concerns time, specifically the time you would have between something happening and something arriving. For most natural hazards we plan for, there is some kind of warning window. Hurricanes are tracked for days before they hit a coast. Volcanic eruptions on monitored volcanoes are usually preceded by detectable unrest for weeks, sometimes months. Even ordinary tsunamis have in many cases ocean-crossing transit times of hours that allow at least some response. The world's emergency planning is broadly built around the assumption that most disasters telegraph themselves before they arrive. A Marsili flank collapse, in worst-case scenarios, simply does not give you that. The window from event to arrival on the Aeolian Islands could be roughly 10 minutes. The window for Calabria and Sicily, roughly 20. Those are not numbers you can build a comfortable response around. Those are numbers that demand pre-existing infrastructure, pre-existing public education, pre-existing automatic systems, because there is no time in the moment itself to organise anything from scratch. Compare this to global ocean tsunami warnings, where a Pacific event might give Hawaii or California several hours to prepare. The Pacific systems are not perfect, but the timeline is at least workable. The Marsili timeline is not in the same sense. It is at the edge of what biological response can do. This compressed timeline is unique among the major hazards facing southern Italy. Earthquakes themselves give you at best seconds of warning from rapid alert systems, but in many regions there is no warning at all. Volcanic eruptions on the famous Italian volcanoes are typically preceded by detectable unrest. Storms have hours or days. Marsili sits in a different category, a hazard whose primary failure mode can unfold faster than any conventional warning can disseminate, on a basin small enough that the wave reaches populated coasts before most response systems can even fully spin up. The implications of that compressed timeline are uncomfortable. They mean that whatever planning is going to be useful has to happen now, in advance, when nothing is happening. They mean that the public has to know what unusual sea behaviour looks like and what to do about it without waiting for instructions. They mean that local infrastructure, evacuation routes, vertical evacuation possibilities, ferry protocols, has to be in place before the day of the event. None of that is impossible. All of it requires sustained attention, and sustained attention is exactly what an invisible volcano, by its nature, struggles to attract. The time gap is what turns the visibility gap from an academic concern into a life and death asymmetry. If you cannot see the threat, and you cannot get advance warning of the threat, then your only defense is the kind of preparation that you have to make in the absence of any immediate cue. That kind of preparation requires that the threat be culturally real before it is physically present. Right now, for Marsili, that cultural reality is not yet established. That is the gap to close. Part 27. The probability trap. The third asymmetry has to do with how human beings think about probability. We are very bad at it. Specifically, we are very bad at low probability, high consequence events. We tend to underweight them when nothing has happened recently, and overweight them just after something has. That oscillation produces a long-term failure mode that risk professionals call the probability trap. The math on Marsili sits somewhere on the unfortunate side of this trap. The probability of a major flank collapse in any given year is small. Small enough that you can live a long, full life right next to the Tyrrhenian coast and never experience anything more than a beautiful sea. That is the experience most residents have. That experience repeated across decades becomes a kind of evidence. People feel in their bones that the sea is safe. They are not wrong about most days. They are wrong about the day the rare event finally happens. Compare this to other low probability, high consequence hazards. Major earthquakes in places with long return intervals, volcanic eruptions of the rare, society-changing kind, asteroid impacts of significant size. In each of these cases, the right response is, take it seriously without panicking, study it, plan for it, reduce vulnerability where you can. Do not pretend it is impossible, do not pretend it is imminent. Hold both truths at once, which is psychologically uncomfortable, which is exactly why most people do not do it. The honest framing for Marsili is that On any given day, including the day you are watching this, a major flank collapse is unlikely. Over the next year, unlikely. Over a decade, still unlikely. Over much longer timescales, the probability of at least one significant event becomes harder to dismiss. Geological history is full of large flank collapses on volcanoes around the world, and Marsili has the size, the age, the structure, and the activity profile that makes it a candidate for being one of them at some point in its future. We do not get to choose when that point arrives. We do get to choose how prepared the surrounding societies are when it does. The probability trap is precisely the cognitive shortcut that says, because nothing has happened in my lifetime, nothing will. That shortcut works fine in many domains and fails badly in this one. The world is older than any human lifetime, and many of the most consequential events are spaced on intervals that no individual experiences in full. So when you hear someone, possibly even a calm, reasonable expert, say that the probability is low, hold on to two things at once. They are correct, and low probability does not mean no risk. The asymmetry of consequence, particularly when paired with the asymmetries of visibility and time, makes this one of those hazards where calm, persistent attention is the only sane response. Not panic, not dismissal. Attention. Part 28. The current moment. So let's reassemble the actual moment we're in, slowly, piece by piece, the way a detective would lay evidence out on a table, before deciding what any of it actually means. Because the noise around this story has gotten loud enough that the underlying facts deserve a moment of cold, careful air. A magnitude 2.7 earthquake registered at roughly 96 kilometers depth, almost directly beneath the Marsili Seamount in the Tyrrhenian Sea. That is the headline data point, and on its own, it is the smallest possible flicker on a seismograph that anyone could plausibly build a story around. Too weak to feel from the surface, too far down to crack a wall, too small to register on any consequence scale that ordinary life uses. It is the kind of event that, in any given week, happens hundreds of times around the planet without making a single newspaper. A separate moderately deep tremor occurred west of Mount Etna, at a depth of around 33 kilometers. Also small, also routine, taken in isolation. Etna sits inside the same broader subduction architecture as Marsili, and small earthquakes around it are part of how that system breathes day to day. Two oarfish washed up in northern European waters, one in Denmark, one before that in Ireland. Far from the Tyrrhenian, far from any active Italian volcano, far from any seismic zone that has anything mechanically to do with what is happening beneath southern Italy. Two unrelated coastal stretches, two strange-looking deep-sea creatures, two photographs that travelled around the world before the actual context could even put on its shoes. The internet, in its usual pattern, braided these threads together into a single narrative about an imminent underwater disaster. Within hours of the first images going viral, the algorithm was serving up videos that suggested, sometimes subtly, sometimes with all the subtlety of a brick, that these events were connected, that an omen had appeared, that the experts were missing something the ancient folklore had been warning about for centuries. Serious news outlets, to varying degrees, picked up the more dramatic threads of that story, because dramatic threads are what the modern attention economy is built to reward. A careful explanation of intra-slab seismicity does not get clicks. A doomsday fish does. So what is the most defensible conclusion from all of this, when you actually sit down and look at the numbers without the soundtrack? Let's go through them one at a time, and I will be straight with you, because that is the deal we have on this channel. The earthquake is, on its own, routine intraslab seismicity in a known and well-characterized subduction system. The Ionian plate has been descending beneath Calabria for millions of years, and the deep parts of that descending slab generate small earthquakes regularly. There is no specific scientific basis, sitting in the current data, to interpret this individual event as a near-term precursor to anything dramatic at Marsili. None. Not in the official monitoring bulletins, not in the peer-reviewed analyses, not in the public statements of any of the institutions tasked with watching this region 24 hours a day. If this earthquake had occurred at the same depth in the same plate 2 months ago, when there were no fish in the news cycle, almost nobody outside of seismology would have noticed it had happened. The Etna activity is, on its own, within normal background variability for that volcano. Etna talks constantly. It is one of the most acoustically and seismically chatty volcanoes on the planet. A small earthquake on its flank in any given week is the geological equivalent of an old house creaking at night. The sound is real. The cause is also, almost always, banal. The walls are doing what walls do. The volcano is doing what Etna does. The Oarfish strandings are, statistically, not a reliable predictor of anything seismic, however eerie they look in photographs, and however much our cultural memory wants them to mean something. The peer-reviewed work on this has been clear. Across long datasets, Oarfish do not cluster meaningfully before earthquakes. They strand for 1,000 mundane reasons, and we, as a species, only remember the ones that happen to fall before something else dramatic happened. Because human memory is a highlight reel that ruthlessly forgets the misses. Considered together, taken honestly, none of these three signals constitutes evidence of an immediate threat. The Italian National Institute of Geophysics and Volcanology has not raised alerts. International researchers tracking the Tyrrhenian system have not flagged anomalies. The sea is not being told to evacuate. The cruise ships are still running their scheduled routes between Naples and Palermo. The beaches in Calabria and Sicily are being prepared for tourist season, the umbrellas being unrolled, the lemon stands being restocked, the ferries to the aliens being maintained on their normal schedules. From every operational standpoint, every dashboard, every monitoring screen sitting in a room in Rome or Catania or anywhere else, today is a day like almost any other day in the central Mediterranean. That is the calm, accurate, slightly anticlimactic truth. And I want you to sit with that for a beat, because it matters. There is no immediate disaster. There is no countdown. There is no emergency. And yet, this moment is also genuinely useful, and I do not want to undersell why. It is useful because by pure accident, it has pointed a flashlight at a part of the natural system that almost never gets attention. The chain of events that brought you to this video, a small tremor, two unusual fish, a viral pattern, an algorithmically rewarded headline, has, by sheer coincidence, illuminated a corner of European geology that mainstream culture has spent decades politely ignoring. It has reminded the small number of people who do pay attention to these things that Marsili exists, that it is the largest active volcano in Europe, that it sits hidden under 3,000 meters of water in a sea most people associate with vacations and ferry rides, that it has structural risks, flank instability, hydrothermal weakening, gravitational potential, which conventional tsunami warning systems built around the assumption of large detectable earthquakes would not necessarily catch in time, that the coastlines surrounding it are not as fully prepared as the underlying hazard would justify, not because anyone is hiding anything, but because the cultural awareness has simply never caught up to the geological reality. That, in the end, is the real value of this news cycle. Not panic, not prophecy, not omens or fish or fringe theories about electrical fields and ancient warnings. Awareness. A small, hard-earned chance for several million more people than yesterday to know something true about the world that they did not know yesterday. A chance to think clearly, even briefly, about an asymmetry that, sooner or later, will matter to somebody, even if that somebody is not us, even if it is not anyone alive in our lifetime, even if it is a generation we will never meet living in towns whose names we do not yet know. The Earth, in case you needed reminding, is extraordinarily patient. Geological hazards do not get bored and wander off because we lost interest in them. They do not vanish because the news cycle has moved on to a new headline. They do not care about the quarterly earnings of cruise lines, or the housing prices in coastal towns, or the political mood of any given decade. They keep accruing slowly, on their own indifferent clock, in their own indifferent units of measurement, and the only thing that ever changes about them, from one century to the next, is our level of attention. The hazard is the constant. We are the variable, so treat this moment for what it actually is, rather than what the algorithm wants you to think it is. Not a doomsday signal, not a prophecy fulfilled, not a coded message from the deep encoded in the body of a stranded fish, a reminder, a pointer, a small, almost gentle tap on the shoulder from a planet that has been running the same machinery for 4.5 billion years, suggesting, without apology and without urgency, that maybe, just maybe, we should know our local geography a little better than we currently do. That maybe the place where we put our coastal towns deserves the same level of curiosity we apply to the surface of Mars. That maybe the quiet, blue, postcard-perfect sea in the middle of southern Europe has a story we owe ourselves the courtesy of finally hearing. And once you have heard it, The question becomes what you do with it. Part 29. Final Frame. Step back with me one last time. We have covered a lot of ground in this video. Earthquakes, subducting slabs, hydrothermal chemistry, basin geometry, doomsday folklore, conspiracy layers, oarfish biology, and a mountain bigger than anything in the Alps that almost nobody alive has ever seen. But the story we have followed is not, in the end, the story of a single earthquake or a single fish. Those were the entry points. Those were the headlines. Those were the small, photogenic events that gave us an excuse to look at something we usually do not look at. The real story, when you strip away the noise and the omens and the algorithmic excitement, is the story of an asymmetry. 3 of them, actually, layered on top of each other, locking into a single shape, defining a category of hazard that the modern world is not yet emotionally or culturally prepared to think about clearly. Let's name them slowly, one at a time, because each one of them deserves to be understood on its own terms before you put them back together. The first asymmetry is invisibility. The most dangerous active volcano in Europe sits in a place where you simply cannot see it. No city skyline contains it. No tourist postcard depicts it. No travel show opens with a sweeping aerial shot of its summit. It does not appear in the background of vacation photos. It is not in any guidebook you would buy at an airport. Children growing up in coastal towns within its potential impact zone are not taught its name in school. It is an enormous 80-vent volcanic ridge, taller than peaks in the Alps, whose summit sits half a kilometre beneath the sea, and the sea above it looks, to every passing eye, exactly like the sea anywhere else in the Mediterranean. Boats sail over it. Ferries cross it on schedule. Container ships pass through its waters every single night without their crews having any reason to think about what is underneath them. From the standpoint of human culture, this volcano effectively does not exist. From the standpoint of geology, it is one of the most consequential structures on the entire continent. Those 2 facts coexist, quietly, every day. The second asymmetry is speed. The worst-case scenarios for a Marsili flank collapse involve waves arriving at populated coastlines in roughly 10 to 20 minutes. 10 minutes for the Aeolian Islands, 20 for the coasts of Calabria and Sicily. There is no atmospheric warning of the kind hurricanes give you days in advance. There is no transcontinental travel time of the kind that lets a Pacific tsunami trigger alerts hours before it arrives in distant countries. There is no mandatory felt earthquake to wake people up, to send them outside, to start the news tickers running, to trigger automated alarms across the basin. The system can fail in a way that bypasses every conventional precursor we have built our warning infrastructure around, and the surface of the sea can learn about it only at the moment when the water itself becomes the messenger. By then, of course, the messenger is also the message, and the message has already crossed half the basin. Speed, in this context, is not a feature. Speed is a closing window. And the window, in the worst plausible cases, is shorter than the time it takes most people to find their car keys. The third asymmetry is unpredictability. Flank collapses on volcanoes like Marsili do not arrive on a schedule that human beings can read in advance. They are governed by slow internal processes, hydrothermal alteration eating away at rock from the inside, sediment loading shifting the balance of forces along the slope, gravitational stress accumulating across enormous structural masses, fluid pressure pulsing through fractures we cannot directly observe. These processes can quietly approach a threshold for thousands of years, and then, on a day that no model can specify in advance, cross it in an instant. We do not have the resolution, with current monitoring technology, to forecast that crossing reliably. We can describe the hazard in broad terms. We can map the kinds of waves that different failure scenarios would produce. We can run simulations in air-conditioned offices and publish the results in journals. What we cannot do, honestly, is pin a date. Not next week, not next decade, not next century. The honest answer, on the question of timing, is that nobody knows, and anybody who tells you they do is either selling something or guessing. Layer those 3 asymmetries together and you get the situation we are actually in. An invisible threat, capable of producing fast onset disasters on a timeline that nobody can predict. Read that sentence twice if you need to. An invisible threat capable of producing fast onset disasters on a timeline that nobody can predict. That is not a comfortable framing. It is not the kind of sentence that fits cleanly onto a tourist brochure, or into a real estate listing, or into a politician's re-election speech. It is, however, the honest one, and the honest framing of a hazard is the only kind of framing that lets you actually plan for it like an adult. The dishonest framings, flat denial, full-blown panic, breathless omen chasing, lazy conspiracy theorizing, feel emotionally adaptive in the short term and accomplish exactly nothing useful in the long term. They make the watcher feel something. They do not move a single sandbag. They do not change a single evacuation route. They do not save a single life on the day whenever that day arrives, when the water actually does what the modelling has been warning about. The contrast between signal and reality in this whole story could not be sharper if it had been designed for a screenwriting class. The signals, the things we have spent days and weeks circulating across every social media platform, are a single small earthquake and 2 beached fish, tiny, photographable, shareable, emotionally legible objects. The reality, sitting underneath all of that surface chatter, is a 3,000-metre mountain with chemically weakening insides, hydrothermally fed plumbing, 80 eruptive centres and unstable flanks, sitting in a confined basin surrounded by populated coast. The signals are noisy and emotionally charged. The reality is quiet and almost completely unobserved by mass culture. The signals will fade from your social media feed within a week, replaced by some other strange-looking creature on some other beach somewhere else. The reality will still be there. Tomorrow, next year, the year after that. Long after this video has slipped past the bottom of your recommendations, the mountain will be exactly where it has always been, doing exactly what it has always been doing, with or without our attention. So when this story passes, and it will pass probably very quickly, I would ask you, as a small favour to your future self, to keep one image in your head, not the fish, not the seismograph trace, not the doomsday thumbnail, the map. Imagine the boot of Italy, the toe pointing south, Sicily across the strait, the Aeolian Islands strung out in between like volcanic stepping stones, and right in the middle of that stretch of water, completely invisible to every passing ferry and every soaring drone and every satellite photograph the average person ever sees, a giant ridge, taller than peaks in the Alps, 80 mouths along its spine, hydrothermal vents pulsing slowly in the dark, flanks that are evolving on a timescale we cannot fully track, a time horizon that nobody, however well-funded, can clock. That is the actual subject of this video. That is what every piece of noise has been quietly pointing at all along, even when the people generating the noise had no idea what they were pointing at. And so, here is the thought I want to leave you with, the one that I suspect will sit with you the longest after the credits roll, after the algorithm has moved on, after the next strange-looking fish washes up on the next strange-looking beach somewhere else in the world. The day that Marsili finally does the thing that all of the modelling has been quietly worried about, there will not be a meaningful warning. There will not be a felt earthquake to set off the alarms. There will not be a strange flock of birds, an unexpected cloud over the Aeolians, a viral video of a doomsday fish that the believers can later point to and say, "See, we told you." Those things make the news because we want them to. They are what we look for, because they are what we can see. The first sign won't be shaking. It will be the water already moving. This has been Project Nightwatch. Stay curious. Stay calm. And the next time someone tells you the warning sign is the fish on the beach, remember the mountain you cannot see.